A concept that suggests we can traverse vast distances in the universe in the blink of an eye by connecting distant points in space through a shortcut. This phenomenon, known as a wormhole, holds the potential to revolutionize the way we perceive reality. The first theoretical form of a wormhole to emerge was the so-called Einstein-Rosen bridge, which naturally arises from the equations of general relativity. It predicts that a black hole, instead of being merely a matter-devouring monster, could be the entrance to a tunnel connecting our universe to another, or to a distant region of our own. If a massive star collapses under its own gravity, it could generate a singularity, which is a point of infinite density surrounded by the event horizon, from which nothing escapes, not even light. If this singularity were mirrored, it could create what is called a white hole. Unlike a black hole, a white hole would not allow anything to enter. It would theoretically expel everything that approaches. An Einstein-Rosen bridge, which is a shortcut in spacetime connecting two distant points in the universe, links these two phenomena, forming a kind of shortcut between two parallel universes. But don't get your hopes up. If you were to throw yourself into a black hole hoping to come out on the other side, you'd meet a tragic fate. The extreme gravitational effects would cause what's known as spaghettification, where the difference in gravitational force between your feet and your head would literally stretch your body until it is torn apart into atoms. Additionally, the time required to traverse an Einstein-Rosen bridge is infinite. The tunnel would close long before you reach the end. In other words, these shortcuts are not useful for interstellar travel. To avoid this fate, we would need something that could push the walls of the wormhole apart to keep it open. This is where the so-called exotic matter comes in, which would have negative mass. Unlike anything we know, this form of repulsive matter would push objects away instead of attracting them. It would be the equivalent of an anti-gravity device, essential for sustaining a stable wormhole. Modern physics has yet to confirm the existence of exotic matter, although there are some hypotheses involving the quantum vacuum. Contrary to what the name suggests, the vacuum of space is not completely empty. It is filled with quantum fluctuations where particles and antiparticles constantly appear and annihilate each other. These fluctuations could theoretically be manipulated to produce the necessary effects to stabilize a wormhole. Even if a traversable wormhole could be created, there would still be several other issues to resolve. For example, the violation of causality. If a wormhole connects 2 points in space, it also connects 2 moments in time, creating the possibility of time travel. This could lead to paradoxes such as the famous grandfather paradox, where a person travels to the past and kills their grandfather before he meets their grandmother. In this way, the existence of the person's parent, and consequently their own existence, becomes impossible. This creates a temporal paradox and a logical conflict of existence when altering past events responsible for their existence. This ability to break time suggests that if wormholes exist, the universe may have mechanisms to prevent their use for avoiding such paradoxes. Like Novikov's self-consistency principle, any event that could occur and cause inconsistencies in the past would simply be impossible. As complicated as it seems, there are theories that go a step further. String theory proposes that subatomic particles are actually tiny vibrating strings, and their different vibrations define their properties. For the theory to work, the universe would need to have extra dimensions beyond the 4 we know, 3 spatial and 1 temporal, up to 10 or 11 dimensions. These extra dimensions would be very small and curled up in structures called Calabi-Yau manifolds, so tiny that they are imperceptible at everyday scales. It aims to unify general relativity, which describes gravity, with quantum mechanics, creating a possible theory of everything that would explain both the large-scale universe and the microscopic world. Additionally, it suggests that our universe could be a brain floating in a larger space with other universes and that microscopic wormholes may have formed shortly after the Big Bang. These tiny wormholes, with their ends scattered throughout the universe, may be out there, but they are so small that we have no way to detect them. To use them for travel, we would need to find a way to expand them to a macroscopic size and stabilize them with exotic matter, a challenge that is currently beyond our technological and scientific capabilities. Although we haven't found concrete evidence of matter with negative mass, we have already manipulated the effects of the quantum vacuum, where pairs of particles and antiparticles spontaneously appear and quickly annihilate each other. Scientists speculate that we could use these effects to create a pressure that mimics the negative mass needed to stabilize a wormhole. This is just theory, but not impossible. However, even if we could produce exotic matter in the laboratory, keeping a wormhole open would require pressures far greater than those found inside neutron stars, the densest objects in the universe, surpassing anything we can imagine or create with current technology. There's also another intriguing idea. Some scientists suggest that the supermassive black holes we find at the center of galaxies, like Sagittarius A** in the Milky Way, might actually be disguised wormholes. The appearance of a wormhole would be similar to that of a black hole, a spherical region surrounded by a disk of distorted light. This is because both black holes and wormholes bend light around them in a similar way. The difference lies in what happens when crossing the event horizon. While a traditional black hole shreds anything that crosses its boundary, a wormhole would theoretically allow a safe passage to another part of spacetime. The problem is that, so far, we haven't found concrete evidence that wormholes are more than mathematical constructs. On the other hand, physics often surprises us with discoveries that turn theories into reality, as happened with gravitational waves, which were predicted by Einstein in 1918. These are ripples in the fabric of spacetime caused by violent cosmic events, such as black hole collisions or supernova explosions. According to general relativity, these extremely energetic events create distortions that propagate through space as waves, carrying energy. Einstein suggested that these waves would be very difficult to detect due to their weakness, but in 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection, confirming their existence. We could be in a similar situation with wormholes. It may be that in the not-too-distant future, new technologies and observation methods will allow us to detect subtle distortions in spacetime that reveal the existence of these cosmic passageways. But what would you like to know about the universe? Leave a comment, and who knows, your idea could become a video here on the channel. I'm keeping an eye on the comments. See you in the next video.